I'll go to Sears. I do shop for you. Yeah, because that's about it. Tempting me.
Tempting you. Yes, sir.
Can I ask a homework question for you?
What you got?
It's like
12.5 number 41.
Ooh, 12, 5, 40. I'll be in like a sweatshirt. Sugar gang. I'll take this. What?
Caleb, I'm sorry, I already lost it. 41? Yes.
I'm sorry.
That I made you on.
Oh. I'm not going.
You guys, this is purely fictitious, isn't it? I mean, you haven't seen it anywhere, have you?
Fine, but.
I said, this is purely fictitious. You haven't seen this anywhere, have you?
Resistance and capacitors.
Capacitors. Thank you. Electrical circuits, particularly those hooked up in parallel. Not serious.
God, I've never
Even
seen that
resistance.
before in my life.
Really? Total resistance?
I remember it's like.
Never mind. This is a math class. I'll stop.
Oh, okay. Yeah, I'm not in 4B yet, so it doesn't mean anything to me just yet.
You guys, I think you have choices. I think you have choices because, what number is this?
41.
Oh, okay, maybe you don't have choices. I thought maybe he gave you exercise 44 first, and he didn't. So I guess I'm kind of stuck. He implied, no pun intended, he wanted you to explicitly find the partial for z with respect to x. I can't do it yet. Because I think if I'm going to answer his question, I need to isolate z completely. Although I got to confess, if we had a differentiation, where he slipped into you on exercise number 44, we could do it another way.
He talks about it in the text also.
No, he only talked about it in text in terms of a function of 2 variables, not 3. So number 44, he introduced in terms of 3 variables. So everybody, check this out. In this equation, if I were to solve for z, I don't know, what would I get? What I get that z is equal to, oy, oy, oy.
I really. Let's see.
All right, we'll crank it out.
1 over x plus
I got a better idea. What's 1 over z?
1 over x plus 1 over y.
Is it?
Minus 1.
You know, we offer a course on campus, really a good course to take. It's called Math PE. So I'll subtract 1 over x. Sorry, that was a joke. I really didn't solve it. Minus 1 over y. However,
Take the inverse of that.
I don't want to use too many fractions. Well, how I rewrite it with 1 fraction. I think that means 1 over z is nothing more than yay, yay, yay. Is that an xy? Minus x minus y over x1.
Sure.
Now you're giving up. And that being the case, I think z is nothing more, if you believe me, is nothing more than the ratio of xy to this difference.
Did you jump there, way over there, in your head?
Stupid math T. And so for me to find the partial of z with respect to x, I got an idea. Answer this simpler question. Do I have to use, or excuse me, am I going to be using the quotient rule?
Yeah.
Yeah, I think so, because even though I'm putting on mathematical blinders treating y as a constant, I do think I got a ratio of 2 functions in terms of x.
Yeah.
So diving in, using my quotient rule, I have nothing more than what the heck you see upstairs. I misspoke, didn't I? What the heck you see downstairs. Times the partial of the numerator with respect to x. You guys help me.
Why?
Yes or no? Product rule?
No.
Heck no, treating y as a constant, I think the partial of the numerator with respect to x is merely
Why?
I agree. Minus, what the heck I see upstairs, don't touch. Times the partial of my denominator with respect to x, treating y as a constant, what do you get?
Y minus 1 minus y.
I agree. Is it okay?
Wait, no, it's y minus 1 minus y, isn't it? Oh, but no, that's goes to 0, okay.
And I think downstairs I got my denominator twice. That being the case, I think the partial of z with respect to x can be re-expressed, let's see, you guys, can we take a couple shortcuts? Watch. Mr. Yin, isn't that xy squared?
So it's gonna be negative y squared plus 1.
Yeah, that's a negative xy squared. Here's a negative xy, but there's a positive xy. Am I not merely left with a negative y squared?
Plus 1.
Oh,
No, never mind. It's negative y squared.
Yeah, you tell me if I made a mistake. Did you guys see it? Okay.
Is that your final answer?
Yeah, what did he write as his answer?
Negative z squared over x squared.
Negative z squared over x squared. You know what? I was thinking that he was going to go into higher dimensions with example number 44. So you guys think he used a different form in the book?
Yeah, see,
What
write
section is
this,
Oh, what kind of?
so if you said just, by this business.
And I will. Before I do, Caleb, can you tell me what the answer is? I just want to first justify
This was
that.
the answer.
Maybe my answer the same as his, because he came up with, oh, I wrote it on the board already.
Don't we really just have to see if whenever z pans out to equal whatever the crap is that you're trying to do that?
I agree. You guys do this for me. How would I justify that these are equal to each other? Or maybe justify they're not equal to each other?
What I just said?
Yeah, you just pick z up off the import over there, slap it in here, clean it to fractions, you can get the same thing. Can I show you guys what the author did, since this answer looks so much different than mine? Without giving you the formula, can I derive it out of thin air? Because I don't want to slap it on the board and say deal with it. So humor me for a minute.
I didn't write that down yet.
Oh, you didn't write this down?
Did you write that down? Oh, yes.
Yeah, someone did, because I made the example up out of thin air.
Yeah, there's like, 28 of us probably that wrote it down, so.
Z was equal to, I don't remember.
X squared y plus xy cubed.
Sorry, Linda. And the first question was, find the directional derivative du bar
You actually,
at the point.
1, 2.
yeah, you didn't actually put du bar.
I know, I'm just trying to abbreviate it. In the direction of
3,
3
negative 1.
negative 1.
3 and negative 1.
Yeah.
Whoops. Not that it matters what I wrote on the board, I could have made up new numbers, who cares? Do you guys think I can come in and maybe erase the middle?
Yeah, sure.
Alright. So you guys, in deriving his formula that you guys are going to see on the bottom page 825, I just want to suppose that I've got an equation like this. In other words, I want you guys to consider an equation that can be expressed as some junk in x and y being set equal to 0. For example, what did he have in this example, this question? Was it 1 over x plus 1 over y
Plus 1 over 0.
is equal to?
1.
Now, technically speaking, when you look at this equation, you can think of this as an equation in the form z is equal to some function in 2 variables. You could. And so if I were to differentiate z with respect to t, excuse me, I misspoke, with respect to x, I can think of this as the partial of z with respect to x times the derivative of, jeepers, what's next?
Y.
Well, if I treated x as my independent variable, using the chain rule, wouldn't it just be this? Plus,
Is that dx over dx?
yeah, I'm being careful. These are d's, These are partials.
Okay.
Plus, I think the partial z respect to, well, the other intermediate variable times dy dx. Now, if I were to isolate dy dx in my equation, wouldn't I get this? So isolated what you see circled. Looking at this particular equation, if this really is the output of my function z, then what can you say about its derivative? If z is set equal to 0, what's this derivative? It's just 0. So if I subtract this beast from both sides, divide by the coefficient, am I not merely going to give me the partial f with respect to x over the partial f respect to y? Oh, but wait a minute, I subtracted. I get a sign change. So in other words, a shortcut for performing implicit differentiation when you're given an equation in those three variables. And I gotta confess, if you guys take a peek at the homework set, if you extend this down to example or exercise number 44, he just jumps into a higher dimension. And I think, if you guys want to use this formula, the amount of work you do is a lot less than what I did on the inkboard when I differentiated explicitly. Because implicitly, let's take a peek at what we have. What can you say about the partial with respect to x? What does it end up being? What's the partial of f with respect to y? Say a little louder. You guys agree? Do you agree?
Well, it doesn't give us the right answer.
No, so what's wrong?
The partial with respect to y isn't 1 over y squared.
What is
It
it?
would be 1 over z squared or negative 1 over z squared.
Well, I admit z is a function in that variable. But if I'm going to use this formula, which is a formula you guys have on page, I forgot where it was. If you have your text, if you're looking on the box on page 825, it's there in 12.9.
They were asking us to find dz dx.
Oh, was it? Did I misspoke the question? I'm sorry. What I just derived was the formula he gave you in the text.
That's fine, but we're finding, the problem though is to find dz dx.
Isn't partial z partial y?
Right, I mean partial, z partial.
Then I can't. I can't because technically speaking, I need the formula in exercise number 44. So he really should have had example number 41 after 44. So I think he made just a little blunder in the direction in the order of his exercises.
If you set the equation z equal to 1 minus 1 over x minus 1 over y to the negative 1 power,
Yes.
and then you take the derivative of that, you get that to the negative 2nd power times 1 over x squared negative.
Which is exactly what I did. You're writing it differently. You're saying treat this to negative 1 power and I actually inverted it.
But then you can just plug in the z.
Yeah, but that's hokey. That doesn't save me as much time, unfortunately.
But can't you rewrite the little formula, minus fx over fz?
Yes, I can, which is exactly what he did in exercise number 44.
Yeah.
And so that's why I'm saying it's a little bit hokey because technically speaking, he didn't derive this formula yet.
So what's the dx up there, partial z, that's an answer, and you're saying another.
Yeah, I'm just simply saying these two beasts right here are equivalent.
And so is there a reason we would want to do one over the other, or just?
Absolutely not. I have no preference for it. But again, you guys, I'm just trying to press upon you. He really didn't give those formulas till exercise 44, and this is number 41. So I was just simply answering the question directly because that's what those are the tools we have. You guys, I'm sorry, I ran in here from the parking lot, so I'm really hot.
I was gonna ask, is dx over dx equal to just 1, or does it cancel out to 0?
Yeah, when I use this dx over dx, I'm really saying this. This represents the derivative with respect to x of whatever the x is. But jeepers, you because I'm differentiating with respect to that variable. Piece of cake. That's why I just admitted it. I didn't write it.
I don't feel like any of the homework was on implicit differentiation.
What section 12.5?
Yeah.
If I said implicit differentiation, I mean the chain rule,
Right, I'm just asking this implicit, is that someone need to know, what your sections?
Not necessarily,
Okay.
because you can get around it. He slipped in for exercises 27 through 32. Implicit differentiation for equations of only two variables, which by the way is nothing more than using, I've lost it everybody, right here, this equation. But I gotta confess, this simply allows you to redo what you did back in Math 30 because we learned how to implicitly differentiate. We're just stating it a slightly different way. So when you look up exercise 27 through 32, it is implicit differentiation. If you take a peek at the exercises after 44, there's an example where I've got implicit differentiation. I'm just raising by one more variable, jumping into one more higher dimensional space. So, hey, if I said implicit, I meant the chain. That's what I meant. Which is exactly what I used here.
So when you have the f of x and f of y over there, that doesn't get you that answer. So do we solve why that is?
Yeah, because he's using actually the formulas you will see in number 44. So dive in there, use those formulas if you want, and you can derive your answer to be looking like this, but this is equivalent to my answer.
And what about that answer? Is that something?
That doesn't apply because we're
Okay.
dealing with an equation, only two variables,
Okay.
and he had three. So sorry for his misplaced exercise.
So would you solve for z then? Or is z equals that and he could do that?
Which is exactly what I did, yes. Yeah. You just, at this stage of the game, cool.
Okay.
Guys, anything else? Before I go to my first question. So, I get to use my first question within 10 minutes. Sorry, I take that back. Coming back, let's talk about the surface. And by the way, you guys, I made up an example I think is sophisticated enough where if you don't mind, I'm not going to graph the surface in space. It's not one of our basic graphs in terms of our common surfaces. However, if I were to compute the directional derivative relative to what you and I talked about last time, do you guys agree? This directional derivative at any value of x for this particular u bar could be interpreted this way. You guys just humor me. Relative to what you and I discussed last time, is that okay? I'm hoping your answer is no. But tell me why the answer is no.
Wasn't it, the dot product of the partial, or I forget what it's called, but the partial, derivatives of those two, times the unit vector of,
Thanks, that's the problem. I may be multiplying by a vector in the appropriate direction. It's just that this u bar has to be unit vector. For this reason, you guys, I've got some surface in 3 space. And I wanna plant my feet at a point x comma y in the xy coordinate plane. I want to walk in the direction of the vector 3 comma -1, but I only want to walk 1 unit so I can see what the corresponding change in the z values is, walking 1 unit horizontally or vertically or somewhere in between. That way the ratio of the change in z to 1 is indeed going to be the derivative function's value. And I confess, I sometimes in class will reinterpret this or rewrite this as del f is just simply represents the gradient vector. But in terms of a computation, don't you guys agree I have to divide out by the magnitude? Are you there? No. Oh, you're not. You don't like that.
So it's del, why are you dividing out by the magnitude, I guess is the only thing I don't get.
Here's why.
Because you just want to do it.
Back in the xy coordinate plane. Your question is too important to miss or to ignore. So I got a tangent line to my graph. I know what the slope of the tangent line is. And now looking at my picture, this means to move from this position to this position on the x-axis, my z value is going to rise 3 units. Do you agree with that? On the tangent line. From here to here, my z value is going to increase by 3 units.
No.
What do you mean, no? Why not? What did I do wrong?
3 rise
So I think I made a mistake. I think the rise of my z value is gonna be 3 for every row of 1 unit in the x-axis. So when I talk about a slope being equal to 3, or even a derivative function evaluated at some value of x called phi, being equal to 3, same thing, it simply represents that if I walk horizontally 1 unit in the x direction, I'm gonna rise my y values by 3 units. That being the case, when it comes to some surface in 3-dimensional space, x-axis, y-axis, z-axis, here's my surface, whatever it looks like. And I've got some point, say, a comma b. If I want to talk about the corresponding change in the z values of my surface described by this equation right here, if I want to talk about the change in the z values, move in the direction of some vector u bar at that point a comma b, it means down in the xy coordinate plane, I'm following u bar but only as a unit vector so that its magnitude is +1. And talk about the corresponding change in the z values, whether it be positive, negative, or maybe neither. And so that's why, Eric, it's got to be a vector, so they talk about the corresponding increase in z values for 1 unit change in the xy coordinate plane, whatever the direction u bar is.
But you know it's that direction.
I made it up out of thin air.
Okay, so.
I say consider walking in this direction in the xy coordinate plane and tell me how the z values are changing.
Okay.
So, I think I have an answer to the question, you guys. Darn it. I guess the gradient vector is going to end up being, I don't know, you tell me. I said, I don't know, you tell me.
36 over 10.
Say it again. The gradient vector?
12, 13.
Wouldn't it be 2xy plus, man, do I feel alone.
Plus y cubed.
Plus y cubed, comma.
X squared plus 3x squared.
So it's a 3xy squared. Times my, is that going to be a root 3, or excuse me, positive 3 over root 10? Comma negative 1 over root 10, when x is equal to, I forget the numbers, is it 1 and 2? All right, you guys, I'll plug my numbers 1 and 2 in for x and y respectively. I think that merely gives me, ay, ay, ay. Is that another 12? No, it's 13.
2 times x times y, and x is 1 minus 2 would just be.
Wait, I'm sorry, why are you plugging those in?
Because I want to know how the z values are changing at this particular point in that direction.
Oh, when, I want to see that part. So you're actually
Yeah, you guys just double check my arithmetic. Oh, by the way, the dot product is not a vector. The dot product is actually a scalar. And so I think, yeah.
When you say du at 1, 2, is that a point in free space?
It is, no, it's a point in 2 space. And
Okay.
here's why.
All right.
Because when it comes to the directional derivative, for the surface z being equal to a function in x and y, I want to plant my feet in the xy coordinate plane, look at a direction, walk 1 unit in that direction, and see how the corresponding z values are changing.
So this is an x and a y value.
It is. It necessarily will be an xy value, because I want to know how these things change relative to moving around in the plane involving those 2 variables.
Okay.
Sort of like my picture over there. That's why the a comma b is in the xy coordinate plane.
Okay.
If your vector's like 3t and like t cubed to the t.
Ooh, what a good question. Sometimes I'm going to have to worry about that because I want to look at the magnitude of the vector, the directional derivative. I'll get there with an example before we're done today. All right, if you guys are okay so far, let me finish. Numerically speaking, I guess that merely gives me, is that a 40, a 36? Minus 13 over root 10?
Correct. 23 over root 10 is a nasty little number.
Is it what?
A nasty little number that I can't do in my head.
I think it's beautiful. It's approximately 23/3. And if you guys are okay with my arithmetic, oh shoot, I just talked too much. You talk. What tech does that number represent?
That's the change in z.
So it's a change in the z values when you move in the direction of the x-axis.
No,
No,
it's
no,
the
just
change in
the change in z when you move in the direction of
3, -1.
3, comma negative 1 is a vector when you're at the point 1, comma 2 in the xy coordinate plane. Do you see me putting it all together? If you do, that was part one, let me change it.
Oh, wait.
Yes, oh wait. Sorry, ma'am. Did you get the first line?
Yeah.
Okay.
So you said that that's the change in the z values when you move in the direction of 3, -1, and you move 1 unit in the x and 2 units in the y.
I agree, but you know what, now that you're repeating my words, I gotta confess to you guys, I am misspeaking a little bit. When I said that is a corresponding change in z values, it really is just an approximation to the change in z values, do you not agree? Sort of like with a tangent line for a curve in 2 space, that the tangent line approximates the curve really well locally speaking. The further I get away from that point of tangency, the worse the approximation could be. And same thing here in higher dimensional space. What about my modifying or extending my question? At the point, what was point 1, 2? And the xy coordinate line. In which direction?
Is that an at symbol?
Yes, it is. It is. In which direction? Should I move? To experience. The greatest rate of change. For z. I might rephrase the question using the phrase, the greatest ascent. Anybody?
Go 13.
Set the,
You move parallel to the gradient.
yeah, I agree. Because I think the direction of the gradient vector is simply going to give me the direction in which I'll get the greatest ascent for z values. And so I think the answer to my question is nothing more than this. The gradient vector for f evaluated at the point 1, 2, which we've already computed as nothing more than 12 13ths, or is 12, 13, excuse me.
And how did we get that? 12, 13, sorry.
I was just evaluating the gradient vector at that point. Do you guys see why the gradient vector gives you the direction of the greatest ascent?
I don't see why it's the greatest.
Ooh, okay, too many blank stares. I need room. Can I get rid of the middle board? You guys, if this is my working formula for the directional derivative in the direction of u bar, this one right here, is it not true that I can reinterpret that dot product as nothing more than the product of their magnitudes? That's multiplication, by the way, not dot product. Times the cosine of the angle in between those two vectors? Now, I gotta confess, you guys, I'm being a little silly. Technically speaking, with this u bar, it's a unit vector. What's its magnitude? 1. So I think all I really get is a magnitude of the gradient vector times the cosine of theta. Oh, shoot, we gotta hold on a minute. Actually, with this factor right here, I think that factor is gonna be no more than positive 1. Because the cosine of any angle is between -1 and positive 1. And so I think the greatest value for this particular mathematical beast right here is nothing more than the magnitude of the gradient vector. And by the way, this cosine value being equal to positive 1 is going to occur when theta is equal to 0 radians. And if the angle between u bar and del f is going to be 0 radians, it means it is in the direction of del f. That's really going to give you the direction of maximal increase, or the greatest ascent. By the way, that's a good question which I did not ask. What is the value of the greatest ascent? At that point, I've lost it. 1, 2. Anybody?
25.
Where'd you get this so fast?
12 plus 13.
Well, I think the answer would be this.
Yeah, wouldn't it be,
Wouldn't it be its magnitude?
yeah, so it would be
So it would be the
144 plus 106.
Yeah, that's square.
You guys get my point. Ooh, let me not write this question on the board. Let me just see if I can ask it. and see if you can give me the answer just like that. So try to answer this question before I finish my sentence. At the point 1, 2. Any
35.
In which direction do I get the greatest descent?
Negative del F.
Thank you. In other words, negative,
Negative 13, negative 12?
well, negative
That.
Negative 12.
12, negative 13. So I'm not gonna transpose those. Yes, no, hello, anybody? You know, there's another way you could look at this. Here's a level curve. And here's another level curve. The direction at this point right here, in which I move to get the greatest ascent, if this level curve has z value, if I'm making these numbers up 2, and this one's gonna be 3. So just level curves of surface, described by the equation, z is equal to a function f in x and y. I think at this particular point, the direction I move to get the greatest ascent is simply perpendicular to the tangent line. They're going to meet each other at a right angle. However, once I get to this curve, I think the gradient vector value at that particular point is going to be pointing in a different direction. But it will necessarily be perpendicular to its tangent line. What do you think? Ooh, Eric, you don't like that.
No, I was writing down when you started, so I kind of came to in the middle of your explanation of whatever it is you were explaining, so I don't know what it is that you're trying to say.
I'm saying this, and I haven't really gotten to my punchline yet. I'm just saying, for a surface in 3 space, at a given point on the surface, in which direction do I move to get the greatest ascent? Well, you just compute the gradient vector. But you gotta confess, looking at the level curves instead, if this is the level curve when z is equal to 2, here's a level curve when z is equal to 3, plant your feet at that point. Roughly speaking, in which direction are you gonna move to get that greatest ascent? In which direction will the gradient vector be? Well, it'll be going in the direction that's basically perpendicular to the tangent line at that particular point. That's all I'm suggesting.
It seems to me like it should be, I don't know, just logically thinking about it, the shortest distance between the 2 lines.
You know, in a sense it is, but I'm nervous you're going to say the following. Well, that's the shortest distance. Or maybe right here.
Well, from that particular.
Now that's
point.
better, because I think we've got to fix our feet at this point right here. But I think the reason why it's deceiving in my picture is I got these level curves separated pretty darn far. These level curves are separated by 1 full unit. Now if I came in here and drew all the other level curves when z increases by maybe 1/10, then you're going to see a better path in which I move to get the greatest ascent. It's kind of deceiving here only because my z value has changed by a relatively large amount in the positive one. That's why it's deceiving in the picture.
I see.
Oh, you guys. How about another question? Sorry I'm so slow. And you guys, again, here too, I truly am just making these numbers up out of thin air. Any ideas?
Gonna have to work backwards.
What do you mean?
We take that del F.
All right, I will. Hold that thought. I'll just compute my del F. The del F, yet again, even though we've already computed this, I just erased it though, I don't remember what it is. Is that a 2x and y? Plus y cubed, comma, x squared plus 3x y squared. What about it?
Well, I imagine that if we were to set it equal to 1, 3 and solve, then that would give us the points x, y, where this del F is equal to 1, 3.
Very nice. But you guys, when I write this on the board, I'm going to make one small mistake. And just tell me where it is. I think I should set this gradient vector equal to the direction I want to point in. Which means I have got 2xy plus y cubed, comma x squared plus 3xy squared being equal to 1, 3. But you guys, I think I made a mistake. Where is
Did
it?
we miss an x squared? Well, couldn't you just set the x and y components equal to 1 and 3 respectively, and not have to?
Divide by root 10.
Divide by. Well, the magnitude of u bar is going to be
Does it
positive.
have to be a unit vector?
No. As a matter of fact, when it comes to the gradient vector, it's not necessarily a unit vector, most likely will not be. However, is its magnitude automatically root 10? I'll say it again. Is it necessarily the case that the gradient vector has a magnitude which is a magnitude of 1, 3? Yeah, I think the answer is no. I think it's no, so I think even though I want to point in the direction 1, 3, it doesn't mean the gradient vector is going to have the same magnitude. It doesn't mean the gradient vector is going to be exactly equal to 1, 3. It means the gradient vector is going to be some scalar of that vector 1, 3. Do you guys see my point? Everybody?
No.
Oh, you don't. Do this. Back in the xy coordinate plane, I'm at some point a comma b, not that I found that point and I haven't. And I want to point in the direction of 1, 3. Oh, it's this vector right here. Would you not agree that when it comes to the surface, when I look at the corresponding gradient vector, which by the way is simply a vector going in the direction of greatest ascent, the corresponding change in the z values isn't necessarily going to correspond to the length of that vector. I just don't know what the magnitude of the gradient vector is. I just know it's going to go in the same direction as 1, 3.
Oh, well, so, okay, so it's going.
Yeah, is that okay?
So when we generated we wanted it to be just unit vectors of 1 unit, but you could have your x and y values changing with, like, a tenth of a unit, right? So that's
Absolutely.
why you have a different.
Yes, I agree completely. I agree.
So the line is going in the same.
Direction as 1,
grid.
3.
Sorry. So the line is going in the direction of greatest ascent, and the other thing describes the x, 2x, that blah, 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 that stuff, describes the greatest ascent, like the.
I disagree. I think with everything you see above this brace, it simply represents the direction you'll be looking in. At that point, a comma b in the xy coordinate plane, so that the corresponding z values are increased most rapidly on the surface.
So those are the z values, and the other side is the xy values?
See, I disagree. I don't think anything in here is a z value. I think this represents the direction I point in to get the greatest ascent. And I know it's in the direction of 1, 3. It's just as a vector, I don't know if it's necessarily equal to 1, 3. It's going to be some scalar multiple of it. Possibly k could be 1, but most likely not.
So on this question, should it say, at what point on the surface is the direction of greatest ascent
In that direction.
in
Yeah,
the
that's-
direction of?
Yeah, I don't think I had to put the
Okay.
words in, only because it's a vector, so that's really what it means.
Okay.
So how do we find out this k value?
I don't. I give up. I let it go. And it simply suggests that when I create components of these vectors, it just simply means 2x, 1,